So, in the previous class we tried to graphically understand how to calculate the minimum amount of solvent required in a typical absorption column. So, essentially we looked at the slope and we try to decrease the slope till it intersects with the equilibrium curve, and there we said the driving force for mass transfer is 0. So, from that we can calculate the slope, and then we can mark those points, and then we can find the 1.5 times the minimum operating conditions, etc. Alright, but we must also understand that whatever we can do graphically we can also solve mathematically by writing down these equations. Okay, so let us redraw this curve of operating lines and equilibrium curve. We said that we have y versus x. Let us assume we have the equilibrium curve like this. So, we have been given this equations y equal to fx. We know these points, we have x2 and we have y2. So, this is at the exit end, and we know y1 the feed concentrations in the gaseous phase, and x1 is not known here. So, if we draw an arbitrarily operating curve with the slope of ls by gs, this will intersect this y equal to y1 here, and if we said that if we decrease this ls given gs, so if gs is fixed and we want to decrease this amount of ls, then the slope will decrease till it reaches and intersects this y equal to fx curve, which gives us ls by gs minimum, from which we can calculate the amount of solvent required. But let us also try to understand that this is the operating lines. Okay, so we can write down the equation for this operating curves as ls x2 minus x1 equals gs y1 minus y2. Okay, so here in this problem, the most typical problem, y2 is given to us, x2 is known. So, y2 and x2 are known, amount of gs flow rate gaseous phase is known, y1 is known. So, the unknowns are ls and x1, but if we realize that at this location where the operating line intersects this equilibrium curve, we also have this equations y1 equals f x1. Okay, so we have y1 equals f x1. One can also then solve these two equations to obtain ls or ls minimum. Okay, so whatever we can do on graphically, one can, in principle one can also solve analytically, etc. So, from here we can solve ls minimum, and then realizing that we have ls equals 1.5 times ls min, we can calculate ls operating, and once we know ls operating, we can put it back in the previous equations to obtain the x1, the concentration of the effluent, concentration of spent liquid, okay, or the liquid effluent. So, essentially the idea of this small exercise here is that we can solve graphically, as well as we can write down the set of equations, operating line which is linear, y equal to mx plus c form, and the equilibrium curve y equal to fx thermodynamics, two unknowns, two equations. We can determine the known quantities here. All right. So, important thing also to note here that the shape of the equilibrium curve will be different depending upon what type of systems we have, sulfur dioxide, water, ammonia, caustic, right, etc. So, in that case there is a possibility that certain curve which is not exactly concave downward, what we have done in the previous two examples or previous two cases, there is a possibility of a pinch at a locations much ahead of the final exit concentration which were corresponding to y1. In other words, let us see this graph here. Suppose we have equilibrium curve like y versus x, and our equilibrium curve goes like this, and if we concentrate on the same x2 and y2 which we had earlier, and this y1 was given here at some concentrations. Now with this, if you want to draw any operating curve with the slope of ls and gs, ls over gs, and if we reduce the slope, or in other words we are trying to find out the minimum amount of ls, we must realize that we can have a tangent here. See, now please, now notice the difference between the previous case where we had the intersect right here. Right now, because of the shape of this curve, which is not exactly concave, which is not concave downward like this, where we had the intersections corresponding to this y1 right here. So in this case, the pinch occurs right here. Here the driving force becomes 0. Driving force for mass transfer is 0 here, is 0, or what we call this is there is a pinch here. So pinch occurs here rather than here. So in other words, this will give us ls, the slope will give us ls by gs min, and from here again we have to find out 1.5 times ls by gs to determine the operating curve, which will now go like this, and we will get the concentrations which is x1 corresponding to y1. Okay, so idea is that you have to be careful with the type of equilibrium curve, which will vary from the system to system. It could be like this, it could be like this, it could be like this, and each case, if the y1 is fixed, y2 x2 is fixed somewhere here, one has to be very, very careful and with the trying to find out this minimum operating curve where it makes a tangent, where the operating line makes a tangent. If the curve like concave downward like this, then of course there is no problem with this finding this minimum curve. We can directly connect to the last point corresponding to this y1 here. We take the example now for the two cases. One is absorption and one is desorption or stripping. And in one case you will see that we have a curve where there is a possibility of a pinch. So let us take this example, very simple example of a typical absorption column. We have a flue gas which contains a coal gas which contains a solute benzene, and we have been asked to clean this this gas, coal gas, with some wash fluids or wash oil. Okay, and then we want to mark all these operating curves, the mole fractions at the inlet, at the exit, the minimum operating curves, minimum operating line to determine the amount of solvent required. So let us take this example to understand this equilibrium curve and operating curves. So this is the example of absorption. So let's try a vertical. We have absorber. Okay, and it's given that inlet we have coal gas which contains benzene. So benzene is a solute or a transferring agent, from one phase coal gas to this wash oil. This coal gas specification is given here, that we have the flow rate Q, volumetric flow rate 0.25 cubic meter per second. And this flue gas contains 2% volume by volume, V by V of benzene. Okay, so if you go by the previous nomenclatures which we used, we have here GS, we have GN, G1. So this would be a solid free basis, or we can call it dry gas. Of course, there is no moisture. Dry means there is no benzene. Based on benzene, free, solid free basis. So we have GS, we have G1, we have a small fraction Y1, and we have capital Y1, the solid free gas. So these are the four quantities here. Typically we have kilomole per second, or we can also have kg per second just by multiplying by the molecular weight. To clean this, we have been given a wash oil. Okay, and this wash oil is not pure. In other words, if this location is 2 and this is 1 here, this contains small amount of benzene. So we can say that the small x2 is given, the mole fraction is 0.00 0.05. Okay, here is 2% volume by volume, so y1 in this phase is 0.02. Okay, and we have been told that 95% removal is required. 95% removal. So we want to reduce these concentrations from starting with 0.02 mole fractions by 95%. So before we do the calculation, let us mark the specs here: GS, G2, small y2 and capital Y2. Notice we have GS and GS without any subscript because amount of GS will remain the same. Okay, so that's a carrier gas or benzene free this coal gas, which is not soluble in wash oil. Wash oil contains X2, but we have LS, amount of solvent required, L2, X2 which is 0.005, and we have capital X2. Similarly here we will have X1, capital X1, LS, and notice LS without any subscript because LS solid free basis amount of solvent remains the same, and then we have L1 here. Okay, certain properties or physical properties are given here. Molecular weight of this wash oil is 260. Pressure is given 1.07 10 to power 5 Newton per meter square. Temperature is given 26 degree centigrade. Now two important things are given here. One, operation, it says similar to what we did we just discussed a while ago. LS solvent flow rate is 1.5 times the L minimum. All right, so this should from here we should be able to calculate actual LS. So first, before that, we have to find out the minimum amount of L min required. Okay, and B, it says that wash oil and benzene, the system behaves as an ideal mixture. Okay, so before we proceed further, it's a good idea to graphically understand what we want to do here. So the most standard procedure, it's recommended that we follow this procedure, that we draw this schematic of this absorption columns. It's a packed bed, so maybe like to draw schematically like this. So it's a packed bed, signifies that there's a packing, some type of packing. Okay, so we have packed bed, we mark the streams, inlet, outlet, we put the specs there, x1, x2, y1, y2 at both the locations 1 and 2. Whatever the quantities are given, we write down 2% volume by volume. So we say that y1 equal to 0.02. Benzene oil which comes from the top, right, the wash fluid contains certain amount of mole fractions. So we have 0.005 there. Volumetric flow rate is given to us Q 0.25 cubic meter per second. So we mark all these points whatever given to us, and what is not given to us we are supposed to determine. Remember, by graphically, by graph, or by analytically, by writing down the equations. There is no harm. Either of the two methods will work. Okay, even if we don't want to draw or determine graphically, it's not a bad idea to draw the equilibrium curves and operating curves at least qualitatively. Okay, so before we take up, let's complete. Let's try to determine what are the quantities which are given to us. So as we said, y1 is 0.02 small mole fractions. So we can determine capital Y1 solid free basis 0.02 over 1 minus 0.02 equals 0.0204. So what is this 0.024? This is nothing but kilomole of benzene per kilomole of dry gas. So notice this nomenclature, or the terminology dry gas. That doesn't mean that it has a moisture. All it means it's a benzene free gas. So that's the meaning of dry here. So that's generally it's used that this gas or this stream is a dry or it's a wet. Not necessarily it contains moisture. It is specify the solute, which could be anything other than moisture. Okay, so Y1 is known here. Now it says that 95% removal, which means immediately we can say that capital Y2 Okay, this capital Y2, this is 0.0204. So that's what we calculated, and we require 95% removal, so the remaining is 0.05. So we have Y2 as 0.00102, and the unit is same as what we have written here, kilomole of benzene per kilomole of dry gas. So now we know Y2, we know Y1. Okay, small x2 is given 0.005 mole fractions. Wash oil is not pure, it contains very small amount of benzene. We will talk about this in the next example, but let's find out capital X2 here. So capital X2 would be 0.005 over 1 minus 0.005. So solute free basis, and this would be 0.00503. Okay, and what is the unit? Unit is kilomole. So what is the unit here? Let's note down the unit here. The unit will be very similar to what we have in case of gas phase. So kilomole of benzene per kilomole of wash oil, this oil. So it's a benzene free oil, it's not the total amount. So that's the difference between small y1, capital Y1, x1 and x2. More important here is now this thermodynamics. Okay, if you recall, first we have to draw this equilibrium curve. So equilibrium curve in case of this coal gas which contains benzene as an impurity, which we want to remove by 95%. To do that, we have been given this solvent. So you will expect that we require equilibrium curve. Given so much of partial pressure in the gas phase, given so much of mole fraction in the gas phase, how much will be the liquid phase concentration as given by thermodynamics or solubility curve. So you can go to some handout, chemical engineering handout, Perry's handout, Treball, McAbey-Smith, some of the textbook. They do report solubility data at a given pressure and temperature. One can go back to these handouts, refer, do some Google search as well, there is no harm, to obtain this Y versus X. But remember here it says this benzene oil, it acts as an ideal fluid. Now if you recall a couple of lectures ago, we say that if it's an ideal fluid, ideal liquid, it will follow Rawls law. So even the Rawls law for the vapor pressure can be used to determine the liquid phase concentration, mole fraction, given the gas phase concentrations, right? So if you recall that we talked about Rawls law and we talked about Henry's law, both laws. Henry's law we also apply if the concentration is low, all right. Rawls law, which is used for calculating the vapor pressure, given the composition in one phase, find out how much the vapor pressure exerted by the solute, can also be used to determine the solubility data, X versus Y, if we assume it's an ideal fluid, which is what it's given here. So at a given temperature, which is 26 degrees centigrade here, all we have to do is to find the vapor pressure of benzene, right? And then knowing the total pressure, we can calculate this Y versus X curve. So let's write down here that we are assuming ideal solution and we are applying Rawls law, which is Yp equals X P0. So see the difference, partial pressure equated in two phases. So this is the Rawls law and we have equated with this Y to P, partial pressure, Dalton's law, etc. you can call it. Okay, so vapor pressure at this temperature of 26 degrees centigrade, we can go back and we can see this is given as 1330 Newton per meter square. So essentially we have Y P, so we can write capital Y 1 plus Y into the pressure is given as 1.07 10 to the power 5 capital X over 1 plus X. So a small y replaced with Y over 1 plus Y and a small x replaced with capital X over 1 plus X into the vapor pressure, which is 1330. To simplify this, we have Y over 1 plus Y equals 1.25 capital X over 1 plus X. So we have obtained the equation for equilibrium curve. Y as a function of x. Now before we draw the operating curve, remember we are supposed to work on LS and GS, which is kilomole per second or kg per second. Either way one can write here, and we talked about the advantage is here that the operating line is straight. Now the flow rate is given Q, which is 0.25 cubic meter per second. Alright, so all we do, we convert this into kilomole per second for the gas phase. So we have G1, 1 signifies the inlet conditions, 0.25 cubic meter per second. You are applying very simple ideal gas law, etc. 1 is the pressure corrections, 1.0133 10 to the power 5 into 1.07 10 to the power 5. So this is the pressure corrections to calculate at normal temperature and pressure. Temperature is 26 degrees centigrade, 273 plus 26 multiplied by 273. So this gives a normal cubic meter per second divided by, if you recall, 22.4 into 10 to the power minus 3 to make this 0.01075 kilomole per second. That's G1. Okay, so now our problem is over. G1, capital Y1, these two are given here, Y2 is given, and X2 is also given. So the unknowns are the liquid flow rate and the spent liquor concentrations, which is at locations 1, LS by X1. Okay, and also you're supposed to remember we said that LS has to be determined from the minimum operating conditions, minimum amount of solvent required from the criteria which we discussed in the earlier class. Now we are in the positions. So after doing this small calculations, whatever is given to us and whatever we are supposed to determine, now we can draw graphically. Remember, not necessarily we have to solve by graphically. One can write down these two equations for operating line and the equilibrium curve, and one can solve by simple calculations, etc. But it's good practice, it's a good idea to draw graphically and mark those points at least qualitatively. Okay, so let's do this. So we have this equilibrium curve, y versus x, and if you draw carefully from the data, you will see that this curve is slightly convex downward. So the shape of the curve is not exactly linear, it is slightly convex here. We will see the importance of this curve. So one has to be careful in plotting whatever data we have chosen for y and x. You should take as many as data possible to draw this curve very smoothly, equilibrium curve here. Let us mark the coordinates here. Let's say this is y1, which is given as 0.0204, and the concentration is brought down from y1 to y2 equals 0.00102, and corresponding to this y2 we have the concentration of the spent liquor, spent solvent, which is 0.00503. So now once we have x2, y2, on the exercise which we did earlier, one has to be careful to find out this minimum amount of solvent. So you can see that there will be a tangent like this. So this makes a pinch here, and we have discussed in the previous class, previous lecture, that this will give you what do we call x1 min, maximum concentration of this spent solvent. So the idea is that if you try to connect directly from here to, let's say, this point here, connecting like this will give you wrong results. So one has to be careful with the shape of the equilibrium curve which we have drawn like this to find out this pinch here. Alright. So once we draw this tangent pinch here, we have the slope. We can determine LS by GS min, slope of operating curve for this minimum amount of solvent conditions. GS is fixed here. Alright. Once we know this LS by GS, the problem is given that LS by GS operating is 1.5 times LS by GS min. So then from that new slope we can determine the curve like this, and then we can do our other calculations. Alright, we can get actual x1 which should be working here. So let's come back to these calculations from the from the previous the values for G1 flow rate of the gas, one can determine GS first as G1 1 minus Y1, which is, if you calculate 0.01, you will get 0.01051 kilomole per second. All right. LS is given as 1.5 times LS min, which is as good as LS by GS operating is 1.5 times LS by GS min, because GS is fixed here, K mole per second, which we have calculated here. So from here to get LS minimum amount of solvent, or you are supposed to get this slope here. How do we get this slope? Remember, this is a tangent here, and this coordinate is x1 min. This point is x2, corresponding to which we have y2. Here also we can have some y prime, and wherever it makes intersection with the curve, we have this x1. So that to find the slope here, there is a tan theta. Either you go by this segment divided by this segment, or you can go by this segment divided by this segment. All you have to do is to read either x1 min or x1 here. All right. So we can write down the operating line equations at the minimum conditions as L1 x1 min minus x2 equal to GS. So if we choose x1 min here, we have to read GS y prime minus y2, or we can also write LS min if we read write this coordinate. So from the tangent, if we extend and suppose we read this x1 as 0.176, we can also find the slope from here. X1, let's put a star here, x1 star minus x2 equal to GS, we have y1 minus y2. So idea is that, it's up to you, either you read this x1 min from the tangent, or you read this x1 star where it's making this tangent, the intersection with this y1 line, or you either of the two will give the same result here, because we have to find out the slope. So LS min equal to 0.01051, which is the GS, multiplied by y1. So this is 0.0204 minus y2 0.00102 divided by, we have 0.176. So we are reading it x1 star here as 0.176. So we are reading, we are trying to find out the height of this segment divided by the entire segment, which will give the same result for the slope if you go by this. So it's up to your choice. 0.176 minus 0.00503, which is x2. If you calculate, you will get 1.190 10 to the power minus 3 kilomole per second. So this is the minimum amount of solvent required for the present conditions. Okay. We have the equilibrium curves which is given to us. We know the operating curves. Wherever there is a pinch, y will be equal to x, and that point will satisfy both operating curves and the equilibrium curve. So one can obtain x1 min from there also. From that, then go back and put back the equations to obtain LS min. But if you have a graph and you do it nice job, then there is no need to solve analytically. So now we know LS min. We can calculate LS operating, which is 1.5 times LS min, which is 1.5 times 1.190 10 to the power minus 3 equals 1.787 10 to the power minus 3 kilomole per second. Right, writing this is same as saying that slope LS by GS equals 1.5 times LS by GS min. Why? Because GS is the same, so they are the same. So it's only LS which we are trying to find out based on this minimum conditions. So either you go by this or you go by this. Try to understand the graphically. Once you know LS, now again you can go back and put back in the same equations to obtain x1 GS. So same operating line. Now we are rearranging to write GS by LS plus x2. So from here we know LS. We can calculate 0.1190. Okay. So again let's redraw the curve right here again. we have y, we have versus x. We realize the curve is slightly convex down like this. We have marked our points, which is y2, x2, which is known to us. We knew y1. We do not know the slope, but problem says that we have to take 1.5 times the LS minimum. So we draw a curve which is a tangent to this point here. This point will be, of course, x1 min, all right, and this slope will give us LS by GS min or LS min, because GS is fixed. When we take 1.5 times, now the curve will move like this, okay, and the curve, when move it like this is the operating curve. Now we will get x2, x1, which we have just now calculated as 0.1190. So if you know, if you want to solve graphically, that will also work. You know the slope, take 1.5 times to obtain this line, and then read from the graph to x1 as x1, or you solve the operating curve and the equations for the operating curve twice, one for this LS min, you obtain LS min, take 1.5 times to obtain new LS, and again put it back here to get x1. You must do this as an exercise to see that both graphically as well as analytically you get the same results. At least you should do once, okay, because it depends upon the type of the problems or type of the system. Actually, the equilibrium curve may be of different peculiar shape, certain very specific shape, and it may not be possible to work out exactly on the graphically. It's prone to error, okay, drawing the tangent, etc., it invites some error. So very often one would prefer writing a small code or a small programming to solve these equations. This is the way most of the commercial engineering softwares like Aspen, they also work. All they do, they have inbuilt this operating curve, very general operating equation for the operating curve. You choose a system, it makes the draws, it has the equilibrium curve y versus x. It solves these two equations under different conditions, whether it's the minimum conditions or it's the operating conditions, okay, but the idea is the same. You should have physical understanding of this. We take the same example here. What we had here was the absorptions, okay. So there's a transferring component from gas phase to the water, okay, and we try to find out the minimum water flow rates or minimum solvent flow rates, and then we took 1.5 times, okay, all right. Now we can have the different case, desorption or stripping. In that case, typically it's a liquid flow rate which is given, and one has to decide the gas phase flow rate. There also we can have the condition that its gas flow rate is now 1.5 times the minimum conditions. In that case, we will see what happens to the operating lines and what happens to the equilibrium curve, where are these points. So we take this example of stripping column, which follows absorption column, okay. So a stripping column, or what do we call desorption column, okay. So we continue with the previous example on absorption. So what we had here, we had the coal gas which contained benzene, okay, and this gas was cleaned with wash oil. So we had wash oil, and here the concentrations x1 which we calculated was 0.119. The flow rate of this wash oil was given was calculated at 1.787 10 to the power minus 3 kilomole per second, and we had this x2 given as 0.005. all right. So this was 2, this was 1. So we addressed this absorption column in the previous example. So now what happens, this liquid which is rich in this benzene, now this has to be stripped, it has to be removed of benzene. So essentially we have one more column in series with this, and now this spent liquid, now this is pumped and brought as feed or inlet to this column. So this is absorption column and this is desorption column. Okay, so the idea here is that this liquid which contains very high amount of benzene, 0.119, so this is same as this composition here. Now this is cleaned with steam. So in a typical power plant we have plenty of steam available. Composition here is 0, so it's a pure stream. This level is 1, this is level is 2. This is steam is used counter current to this liquid to clean this benzene, so that this fluid, now this contains X1, this amount as 0.005, and this liquid now can be fed to this absorption column. All right, so try to understand what we want to achieve in this desorption column. Okay, so typically what we have in an industries, that we have this flue gas, which was here coal gas containing benzene, and we were asked to clean this coal gas. So to do this we had a wash oil as a solvent, but the solvent is quite expensive. All right, so when this wash oil is used counter currently to remove this benzene from this flue gas, then the spent liquor contains very large amount of benzene. Now this spent liquor has to be cleaned again by a different solvent and fed back to the absorption column, because the solvent is quite expensive. So typically in a power plant we have a steam, so we take this outlet from the first column liquid as a feed to the second column, which we are calling it desorption column. Here we use steam counter currently, so we have the mass transfer, and now this wash of this oil, which was spent liquor, which contained very high amount of benzene, now it is stripped of benzene. Now we get a nearly very pure solvent, and this solvent is now going to be fed back to this previous column. So we had absorption in the first column, now we have desorption in the second column, or we have stripping in the second column. In the first problem we were given that liquid flow rate is 1.5 times the minimum. Now here it is given that gas flow rate is 1.5 times the minimum flow rate, because the liquid flow rate is fixed. Remember in the first case it was the gas amount, flue gas, which was fixed, it was given to us, and we were asked to find out what is the liquid amount. Now in the second case it's the spent liquor, so we know the flow rate of it. So the flow rate of the liquid is known, and we have been asked to calculate the gas amount, given that it's at 1.5 times the minimum flow rate. Okay, so the similar problem, but now we had earlier we had absorption, now it is desorptions. So let's get back to this problem. This is 1, this is 2, X1 is 0.005. Note that this composition is same as this compositions. Okay, and here we have X2 0.119, which is same as X1 equal to 0.119. It's a pure stream, Y1 equal to 0.01. Okay, sorry, here it should be small x1. If you recall, we had this mole fraction as 0.005, so capital X1 solid free basis is 0.00503. This temperature is given 120 degrees centigrade and 1 atmosphere. The liquid flow rate here is given, but GS we have to find out. Okay, and it's given that this GS is 1.5 times GS min. Okay, so this is just reverse to what we had in case of absorption column, where we said that liquid LS is 1.5 times the minimum amount of liquid. Okay, so we have the similar procedure here. Okay, we will follow what we did in case of earlier. First we will draw the equilibrium curve, okay, and this equilibrium comes from the Rawls law. Now if you recall earlier that we assume that benzene oil is an ideal fluid, so we apply Rawls law to calculate the amount of liquid in the solvent in the liquid phase, on mole fraction in the liquid phase given the mole fraction in the gas phase. So given Y what is x, we made use of Rawls law. All right. So we apply the similar law, Rawls law here. However, the temperature is now 120 degrees centigrade. So we have to go to the handbook and get the vapor pressure of benzene at 120 degrees centigrade. So let's draw the equilibrium curve. Okay, so we have this equilibrium curve given as y p equals x p0. However, the vapor pressure has to be calculated at 122 degrees centigrade or 120 degrees centigrade. So the small y mole fraction is y capital Y over 1 plus y equals, we have x over 1 plus x p0 over p. This p0 vapor pressure is 319.9 and this p is atmospheric pressure is 1.101.33. So we have the equilibrium curve y equals 1 plus y as 3.16 x over 1 plus x. So this expression is similar except the coefficient is now is different because of difference in this temperature. Now we have 120 degrees centigrade. Okay. Nonetheless, so now with this, now we can plot y versus x. So we have the similar approach how we address absorptions. Now we can draw y versus x. Now if you draw this very carefully, it's slightly concave here. Okay. So we have drawn y equals fx. Now we are going to mark certain points, y1 x1 and y2 x2. So if you recall, in this desorption column, we know the concentration of x1, the liquid at the exit, because this is a fluid which is going to be sent back to the absorption column, and this x1 was given as 0.00503, and solvent is pure, so y1 is 0. So we can mark this point here where we have this 0.00503 x1 equal to 0.003. All right. Now what is given to us is GS is 1.5 times GS min. Okay. Just compare this to LS equal to LS 1.5 times this LS minimum. Now again here, to obtain this minimum amount of solvent, of course we realize that we have to take a slope of LS by GS. All right. LS is known to us, it's given to us. However, GS is not known to us. We know the concentration here. Now this is x2. Okay, this x2 is 0.119. This concentration is same as what we had the concentration of the spent liquor from the column 1 absorption columns. So we can mark this x2 as 0.119. Just compare again. Earlier we used to mark here y2 because that was the absorption column, that was the conditions given to us. Now we know 0.119 here, and to obtain this minimum, if you recall, again we have to take a tangent because we can see a pinch here. So we have a pinch here which will give us 0 driving force, and we can get LS by GS corresponding to the minimum GS flow rate. Now before we calculate, let's try to understand what happens to the slope of this curve. Right? This curve here, y versus x, and try to understand how does this differ, how does the slope change if we have absorption, and in one case, in other case we have desorptions. So if this is a curve, and if this is a point here, and suppose we draw any arbitrary curve LS by GS with the slope LS by GS. All right. This is our x2 and this is our x1. y1 is 0, it's a pure steam here. Now this is slope LS by GS. Now in this case, try to recognize that LS is fixed and GS is allowed to vary, right? So if we increase GS, then the slope LS by GS will decrease and the curve will move in this direction. This is our operating curve. It's going to move in this directions. If we decrease GS, then slope LS by GS will increase, all right, and the slope will move in this directions. So what happens? Suppose the slope moves in this directions with decreasing GS. So when GS decreases, look at the movement of the slope till there is a point when it makes a pinch here, all right. So this point where it makes a pinch, this will give us LS by GS, which is maximum. So make a difference, make a note here. LS is the numerator, GS is the denominator. Okay. Now we are getting a slope which is maximum. We are looking for GS min, all right, which we obtain from LS by GS maximum. Compare this to previous case where we had LS by minimum, which we obtained from LS by GS min. Okay. Again, let's compare the two, absorption and desorptions. In case of absorptions, we said that GS is fixed. Okay. So if GS is fixed and LS increases, slope increases. So recall the previous situations where we had movement of LS by GS like this or like this. Here the GS amount was fixed. So if we increase LS by GS, the curve will move in this directions. If LS increases, slope increases. Okay. If the slope increases, then the driving force del y increases. Height decrease because now we have large driving force, so we require smaller height to achieve this concentrations. And if H increases, look at this moment of x mole fractions. If we increase the slope from here to here to here, the concentration of X will move in this directions, or concentration spent liquor will be dilute or will have small concentrations. Okay. On the other hand, if we decrease LS for a given GS, then slope decreased, driving force decreased, height of the column increased, and X increased. So look at the economy here, LS H and LS H here. If the amount of LS decreases, height increases. If the amount of LS increases, solvent requirement, then the height decreases. Of course, there is a economy here. There is a cost involved. Of course, we don't address too much on economy and cost in this course. You will have an opportunity to address this aspect in design course. All right. So all we are trying to address mass transfer. We are restricted to mass transfer consideration, but you can see how does the economy or how does the cost make a difference here. If you take a very large amount of solvent in the absorption column, then the height of the column will decrease because we have more driving force. Okay. If we take a small amount of the liquid, then the height of will increase. So there is an optimization of the cost, etc. Okay. Similar situations we have now in case of desorption columns. Now in case of desorptions, now LS is fixed, solvent flow rate is fixed. We have been asked to vary the GS, and now look at the movement of slope. Now the slope is going to make a tangent when it is maximum. So to avoid this, we have been told that GS is 1.5 times the minimum. So LS by GS will not decrease. Okay, if GS is 1.5 times, then LS by GS will be 1 over 1.5 times, and this is the way the driving force will also decrease and the height of the column will decrease. So let's sum up this before we come back to this calculations. So here in case of now we have a stripping column or desorption column, right? So it's good to redraw the curve here, and let's see the slope of this 2, 3 like this. So this is the way it moves, and this is LS by GS. Now Ls is fixed and we change Gs. Okay. So if Ls by Gs, that's the slope we want to address. Ls is fixed. If Ls is fixed, and let's increase Gs. If Gs increases, slope decreases. See, the curve will move in this direction. Slope is decreasing like this. Slope decreases, driving force increases, height decreases, and y2 will also decrease. So we have y and we have x. So given x2, now y2 decreases. So again we see a cost effect here. Large amount of solvent is required, steam is required at the cost of a smaller height. If we take a small amount of Gs, then slope will increase, Ls by Gs, and it will approach equilibrium curve, so the driving force will decrease. As this slope operating curve moves in this direction, it approaches equilibrium curve, so the driving force at any location, this difference decreases, height will increase, and at the same time the concentration of y2 exit steam, this will also increase. So again we see this cost effect here. All right. So one can also do some cost analysis to see that there is optimum amount of Gs or the amount or the height of the column which will give us desired result here. Now we restrict our discussion to the mass transfer. In the design course, some course in design, maybe third or fourth year level, you are going to address this aspect. You will make some cost balance, etc. Okay. So we are in this situation when we approach the equilibrium curve, there is a risk of this operating line making a tangent with the slope with the equilibrium curve, where what we call we have the pinch. So we get Ls by Gs from here, the slope from the location at the pinch locations, and Ls is fixed, so we get Gs minimum. So all it says, we cannot have any amount of Gs smaller than the slope of this curve. So this gives us Gs minimum. From here we can get Gs operating equal to 1.5 times Gs minimum. So see the difference, Ls by Gs is now maximum here. Unlike in case of absorption column, Ls by Gs was minimum. Okay, although Gs is still 1.5 times the Gs minimum. So we must understand the way operating line moves in the stripping column as we increase or decrease the flow rate of Gs, because Ls is fixed. In case of absorption column, now we have Gs is fixed and operating curve moves in this direction or in this direction away from this equilibrium curve, depending upon whether we are taking small amount of Ls or large amount of Ls. So once we have identified this, now let's get back to our numerical calculations. We can write down now the operating line equations, which was Ls x1 minus x2 equals Gs min y1 minus y2. Okay. So Gs min we can find from here, Ls x1 minus x2 over y1 minus y2, and Ls was fixed at 1.787 10 to the power minus 3. We have x1 0.119, this is the concentrations. Okay, x1 minus x2, so this would be 0.119 minus 0.00503. So divide by y1 minus y2, which is 0.45 minus 0. So how do we get this 0.45? That would be your equilibrium curve. From here we have drawn this tangent, okay, and we had this x2 which was given to us, x2 this was given to us at 0.119 from the slope Ls by Gs mean corresponding to this minimum amount of GS, we have this curve, this point given as y2. Okay, so this is the y2 which we have got at 0.45. This is y1 which is 0, so y2 minus y1 essentially. We have flipped this, and we have 0.119, and we have 0.00, very small amount, this x1 as 0.00503. So from the slope, wherever it makes this intersection here, this tangent here, and x2 is fixed, we get y2. We substitute here to obtain this GS min as 4.526 10 to power minus 4 kilomole per second of steam. This is the minimum amount of steam required. Here, of course, the driving force will become 0. Again, we said in the last class that either it's a graphically or it's a numerically. Both you should try as an exercise to obtain the same results. So if you have drawn a graph, then from there you should be careful to draw this correct tangent, take this minimum LS by GS, and then from there you get GS minimum, and then take 1.5 times to obtain this new slope. Or you can still write down the operating balance, the equation of this operating curve, equation of this equilibrium curve, and find out where it makes a tangent. You can do the calculation. You can write down a short programming also. Okay, either way it can be done, but you must try both ways to convince yourself that you are getting the same answer. Okay, so GS min is given, and so we have actual flow rate of GS solvent 1.5 times 4.526 10 to power minus 4 as 6.79 10 to power minus 4 kilomole per second. So now we have the new GS. That means now we can draw LS by GS, new LS by GS. So this is your LS by GS operating curve. And if you draw it carefully, then from this x2, now you will get the desired y2, which should be 0.3 kilomole per mole, kilomole per kilomole. So from the graph we can get directly, if you have know the slope, take 1.5, GS take a 1.5 times, so LS by GS will be 1 over 1.5 times. You can draw the slope wherever it intersects this vertical line, this will give you y2 as 0.3. Okay, or again you can go back to the equations which we wrote here, the operating line equations. From here also y2 can be calculated directly, y1 minus LS by GS x1 minus x2 equal to 0.3 kilomole per kilomole. So both of them will give the same result, either you do graphically or you try to do this calculation. So this is the value of GS, LS was fixed, y1, x1, x2, everything is fixed. Okay, so this is the example we had in case of absorption and desorptions. The idea is equilibrium curve is the same. In case of absorptions, operating curve falls above the equilibrium curves. In case of desorptions, operating curve falls below this equilibrium curve. That's one difference. In case of absorptions, generally amount of GS is fixed. Flue gas, how much quantity we want to remove, we want to clean, that's fixed. And we have been asked to find out optimal LS. Optimal means we have to decrease the LS, minimum amount of LS. So follow the slope of the curve, it hits the equilibrium curve, the process will stop, driving force becomes 0, we get LS by GS minimum, we take 1.5 times as an operating lines. In case of stripping column, amount of LS is fixed, because now we have the spent liquor from the absorption column, right? This has to be treated and sent back to the previous column, because solvent is very expensive, you cannot throw it away like this. So we have a steam relatively easily available in a power plants, less inexpensive. So we make use of steam, we clean this spent liquor. So now when we are cleaning it, it's a desorptions. Now the benzene transfers or diffuses from liquid phase to the gas phase. So now LS is fixed and GS we are trying to change. So when we try to change the GS, now the slope is going to, if we keep on increasing, if we keep on decreasing the GS, then slope will increase, and there is a possibility of this operating line hitting this equilibrium curve or intersecting or making a tangent, okay, depending upon the shape of this curve. That gives us LS by GS. corresponding to minimum GS. Mind you, LS by GS is now maximum. Earlier LS by GS was minimum, LS was also minimum. Now GS is minimum, but LS by GS is maximum. From there we get minimum GS. You take 1.5 times, stay away from this equilibrium curve, stay away from this tangent. From there you calculate GS. And also make a note that there is always a cost economy effect. Although we did not do any calculations, if you try to increase the amount of liquid in case of absorption, the height of the column will decrease, but you have to pay for a larger price of this solvent. In case of desorption column, if you take large amount of steams, okay, you are going to pay for this steam. You have the similar situations, height of the column will decrease because the driving force increases. So there is always a cost on the economy. One has to consider cost also when you take up this design codes, extension of this codes, maybe in the third or the fourth year levels. Okay, so this was example for mass transfer and equilibrium. Next class we take it, we address hydrodynamics.